Welcome to Part 18 of Quick Precalculus Review for Calculus. It's also Part 4 of Unit 2 with a very long-winded name, Inverse Functions, Power Functions, Logarithmic Functions, and Alternative Representations of Exponential Functions, including use of the special number e. Yes, it's long-winded, but it holds together in the context of the compound interest formula, which is what we're thinking about here. Alright, I'm going to go very fast in this video, this Part 18. So if the math is new to you, you're definitely going to want to watch parts 1 through 3 of Unit 2 first. If the Mathematica is new to you, you're probably going to want to start at the beginning, parts 1, 2, 3, etc., where I go through the Mathematica in a lot more detail explaining it. I'm just going to use the Mathematica in this video. Got a lot to do. Hang on, you're going to want to pause a lot and take notes as you need to. We're talking about inverse functions, operational, symbolic, numeric, and graphic relationships between inverse functions in this context. In the last couple of videos, we thought about this equation in the context where r, n, and t were fixed. R was the nominal annual interest rate, n was the number of compounding periods, and t was the number of years. We took r to be 8%, 0.08, n to be 4 because it's quarterly compounding, 4 times a year, and t was the number of years. We took it to be 10. That allowed us to think of this as defining the accumulated balance A as a function of P. It's a very simple function called the direct proportionality because it's constant times P. The graph was a line through the origin. It also has the important property that you should realize as follows. If you double the principal, from say 1,000 to 2,000 for example, you will double the accumulated balance at the end of the specific time period, 10 years. If you triple the principal, you'll triple the accumulated balance. That's a special property that direct proportionalities have. We also solve this equation for P as a function of A. That's the inverse function. It allows us to figure out what principal should we use, what deposit should we make to get a certain accumulated balance. And that was a direct proportionality as well. Now we're doing something different. In this video we're going to consider A as a function of B, where B is defined by this equation here. That gives rise to what are called power functions. So what's the relationship here? First of all, C is this intermediate variable. C I'm letting equal 1 plus r over n. That's the relationship between C and r and n. And then by a property of exponents, these two things are equal, and I can ultimately let B equal C to the n. So the connection here is that B equals 1 over r plus n raised to the n power. Okay, but when you look at this equation here, in this video, in the new example in this video at least, you want to think of B and T as fixed, which is a little weird, especially for the T. You're used to thinking of T as a variable. You might prefer to call it M or something instead of T. B is going to be the variable. Maybe you'd prefer to call B X. But I'm going to emphasize that you can use any letter you want, and for me, when I do the new example, B will be the variable. But let's review the old example. Here's example 2.1. Pause the video, look it over, solve it if you haven't. I'm going to move on to thinking about functions. So here we did the Mathematica code from the last video here. I've got r, n, and t that I can enter into Mathematica by doing a shift return. I can enter the function. This is the direct proportionality that I talked about in the last couple of videos. Mathematica can approximate it. What is 1 plus r over n to the nt power? It's about 2.20804, and f of p then is 2.20804 times p, a direct proportionality. I can use table to create a bunch of points on the graph of f, use table form to display those nicely, and then get into the inverse function stuff. Alright, quick review of all the algebra stuff. Here's the algebra I did to find the inverse function. Here's the original function, a equals f of p, where 1 plus r over n to the nt power again is a constant. This is a direct proportionality. I just divide by both sides by that to get p as a function of a. P equals f inverse of a. This is not f to the negative 1 power, it's f inverse. Do not swap the a and the p when they have a certain specific meaning like this. Alright, you should probably pause the video and take notes on all this stuff. Here's the algebra that I did in the last video to illustrate what happens when we plug one function into the other. The function and its inverse. Here I'm plugging f inverse of a into f. You ultimately get a at the end back. You can do it the other way around. You can plug p into f first and then that value into f inverse. And here I have a few other ways that I've written to visualize this. This is new stuff that I've done in this video. Here are a couple of lines that visualize applying those functions. You go from left to right along these lines to do the order correctly. First in this one apply f inverse, then apply f. And you can do it the other way, first apply f and then f inverse. Here are alternative visuals that are sort of more two-dimensional. There's this one right here that shows the fact that you can go around and around the diagram, and here you have the function machine picture of the situation. You can imagine maybe a crank attached to this box that's representing the function f. You imagine p going in from left to right. You turn the crank and out pops the value of a. You can stuff a back in the other way and turn the crank in the opposite direction to represent the inverse function to go the other direction. And then you can go back and forth to see these properties. Here's another way to see these properties. Okay, I'm not going to explain this much. I'll let you think about what I'm saying here. If you like, it's not absolutely necessary. Maybe you want to ask a teacher what this means. I will say that this circle here is the function composition operator, and it's sort of analogous to multiplication. And even though f inverse is not f to the negative 1 power, it's analogous to what happens when you're doing multiplication by a number times that number to the negative 1 power. ID sort of corresponds to the number 1. I'll let you think about that. I'm going to go ahead and now enter this Mathematica code that creates points on the graph of f inverse. Here we see the table of values for f inverse that match the table of values for f, but in the opposite order. The coordinates get swapped. And then we can use grid and show and plot to make plots of both f and f inverse. You should not plot them on the same set of axes. When they have real life meaning, you should plot them on different axes if you are at least letting the horizontal axis be the independent variable in both cases. Actually, if you want to allow yourself to have the independent variable be the vertical axis instead, you can think of this one graph as representing both the graph of f and f inverse, where you'd want to think about a, the vertical axis, being the independent variable for f inverse. If you wanted to see that, so it's sort of like you're looking at the graph sideways. If you wanted to see it look the ordinary kind of way, you'd have to turn your head sideways and look with a mirror reflecting the graph back as you turn your head sideways. That would make the a-axis be looking horizontal and to your right. I'll let you do that if you want. All right, now I'm going to move on and show you that it does look like there's a reflection property here going on. Even though these are two separate graphs, they look like they're reflections of each other across the diagonal 45-degree line, and indeed their coordinates do get swapped. And if you think about it in terms of generic functions where x and y don't have any meaning, and we take x to be the independent variable in both cases, as a teacher may have told you to do, then because we're not thinking about context, it's okay to graph them both on the same set of axes, and we can see the reflection property. This lambda is my parameter to do the actual reflecting with this Mathematica code. And maybe you want to pause the video and write that Mathematica code down to do this. I also added some other Mathematica code in this new video. This is new here. For a generic situation where f of x equals m times x, and say m is positive, and its inverse function, f inverse of x, equals 1 over m times x, you should think about why those are inverse functions of each other. I can make the slope an animation parameter as well, and I use subscripts here for my functions where m is a subscript. It's an animation parameter for those functions. I have to include the m elsewhere as well to get this animation. You might want to copy that code down. So not only can I use lambda as the animation parameter to do the reflection, I can also change the slope of the original function to see that I always get the reflection property. I can even make the slope of the red graph less than 1 to see that the slope of 1 over m is now bigger than 1 in that case. The reflection property always holds. Here again is the code in case you want to pause the video and write that down. Alright, on to a new example. Example 2.2. It's related, but it's a new example. Suppose you'd like to deposit $1,000 for 10 years into a savings account where interest is compounded quarterly, so P is still going to be 1,000 and N is still going to be 4, and you'd like it to double to $2,000 after 10 years. The question is, what should R be? What nominal annual interest rate R, compounded quarterly, is necessary for such growth? Alright, that's our goal. Here's to solve for R. In solving this, we're going to think about a new kind of inverse function for a new kind of function. We're going to think about this function, where again, b is really c to the n, where c was 1 plus r over n. So in fact, b is 1 plus r over n to the n power. Okay, so I'm going to ultimately solve for b first here, and then I'm going to solve for r based on that fact. But this is a simpler form to think about a power function. Again, b is the variable here. B is the independent variable. P and t are fixed. Think of p as 1,000 and t as 10, okay, if you prefer. So this is like 1,000 times b to the 10th. How do you find the inverse function? Here is the general way to do it for arbitrary p and t. Think about this algebra here. Here, I'll let you pause the video, take notes, is some algebraic confirmations of these properties when you plug the inverse function into the original function and vice versa. You should make sure you understand this. Here are some visual ways to think about this in the new context here. If it helps, plug in p equals 1,000 and plug in t equals 10. That helps you think about it. I'm now going to also do that in Mathematica. I'm going to plug in p equals 1,000 and t equals 10. I do have the alternative notation thing here as well with the circle notation. But we better get going on plugging this stuff into Mathematica. Take note of how I'm doing this here. What's g of g inverse of a? Mathematica does simplify that to a. However, unfortunately, Mathematica doesn't simplify g inverse of g of b down to b completely. I even tried full simplify here. You know this does equal b. So you can in your head see that this definitely is giving us b back. It's satisfying the property that the inverse functions composed together give you the identity function. You can use table and table form to display points on the graphs of these functions. However, these tables are not complete swaps of coordinates. Only in the first and last spots they are. In between they're not, and effectively it's because the graphs are not straight in this context. Then I can use grid and show and plot in ways I've shown you in the past to make plots of these. Look at the first graph. What is that telling you? It's telling you a is a function of b. Really, you should think about b as being a number barely bigger than 1 here. That's the application, is when b is barely bigger than 1. You can find the accumulated balance when you know b. Again, p is 1,000 and t is 10. If you know b, you can find out how much you're going to have after 10 years. You can flip it around the other way. You can figure out what b is when you know a. Once again, p is still 1,000, t is still 10. If a is 2,000, what's b? Actually, we're about to solve that. By solving this kind of equation with the solve command, what value of b will give you g of b equal to 2,000? Alternatively, what is g inverse of 2,000? Solve gives you the answer, a bunch of answers in a kind of not very nice form. Nsolve is easier to understand. There are some complex numbers involved. This is the one we want here, actually. b is 1.07177. Find root can also give you that answer. Here's your initial guess. Ultimately, you can use this equation to now solve for r. Make sure you follow that algebra to solve for r. Here's the Mathematica code that will now do that calculation using this equation right here to solve for r to find the answer to example 2.2. r is very close to 7%, 6.99%. That is the answer to this question up here for example 2.2 if you want to write that down. Pause the video. Alright, the final thing we'll do here is just show you a couple new visuals that illustrate what's going on with power functions and their inverses. Here I'm taking a particular power function, g of x equals 2x cubed, and its inverse function, g inverse of x, is the cube root of x over 2. This code right here will show you the reflection property. The red graph is 2x cubed, the blue graph is the cube root of x over 2. And then I can also do Mathematica code that illustrates the same property in a generic case. Generic power function a times x to the p power, where a and p are positive numbers. Its inverse function, g inverse of x, is x over a to the 1 over p power. I've got that stuff in here. A over p are now, a and p are both animation parameters now. I enter this code. Not only can I animate with the particular values of a and p, but I can change a and p as well. Change the power, change the a, and I'll end the video by just showing you the code, and you can pause the video if you want to write it down.